Okay, we're going to move on to column base plates, column base design. This is one we're going to just give you a very quick overview. At the time we developed this seminar, we knew that the Design Guide 1 was going to be reissued, and due to a very unfortunate circumstance, it was delayed almost a year. But I'm now told that it is out and available. If you're an AISC professional member and have access to AISC's website, you can download this new Design Guide 1, I believe it is, right off their website and use it. If you're not an AISC member, of course, you can purchase the Design Guide. But anyway, we're going to give you a quick overview because that new Design Guide ended up being authored by Jim Fisher and Larry Kloiber, I believe. And they spent a lot of time on it and covered all the different kinds of situations. And we're talking about columns that have just axial load on them, which is the simple everyday case we all get into. The columns that have high shear, tension and uplift, or overturning moment. So those situations can be very common. We're going to introduce you to some of that here today, just sort of give you a preview. But then the important thing is to go back and get that design guide. And in column-based situations, particularly where you have uplift or high shear to transfer, they've got a great design guide that covers all the equations that I'm going to introduce here. Obviously, the column base is a critical element because it's the interface between the steel structure above and the foundation. And I think if you examine damage to buildings in earthquakes, one of the problem areas is not only diaphragms that we talked about earlier, but also column bases. Because there, of course, the frame is going under high inelastic action, and the bases are rotating very excessively, and if they're not detailed properly, they basically will fail. They'll either fail in some non-ductile manner where the base plate will fracture, or the anchor bolt will rip out, or the shear, if there's high shear in the brace frame, maybe the shear isn't handled properly. So it's a real test to design column bases in high seismic zones. As a matter of fact, there's very little out there right now in the code about this, and I think there'll be more coming out later. So you get significant force levels that you have to resist. It frequently involves weld between the column and the base plate. It involves anchor bolts between the base plate and the foundation. It involves grout. It involves transferring large shear forces, potential uplift, a lot of things going on at the base of a moment frame or at the base of a braced frame. And how you model it and how it actually behaves can have a significant influence on the success or failure of that frame during an earthquake or a high windstorm. As we talked earlier, a lot of analytical models take the easy way out and say it's either pinned or fixed without taking advantage of that rotational stiffness that we talked about earlier. Improper boundary conditions can lead to an error in the computed drift and the P delta effect. We talked about that earlier. As far as the design of base plates, you have an option to use A36 steel, which is available up to 8 inches in thickness. And beyond that, you get into grade 32. Or you can use A572 grade 50 up to 4 inch, and then grade 42 over 4 up to 6 inch. Really, it's probably more economical to use the A36 plates. You generally want your base plates to be pretty rigid, because that's the assumption you're making when you design them. So I really see no reason to go to the higher cost of the A572 plate over the A36, so we generally use A36 plate. If you have a space problem and a 4-inch plate or a 6-inch plate is too much architecturally, then you may want to consider an A572, but otherwise there's probably no reason to use the higher grade. So increasing thickness is preferred to increasing strength. That's just an opinion, nothing written in stone there. Fillet welds, though, are always preferred from a cost standpoint over partial joint penetration or complete joint penetration welds. Whenever you can, transfer forces by fillet welds. When you can't, then use partial joint or complete joint penetration. If you're in a high seismic zone, you probably want to use complete joint penetration, not use partially joint penetration welds because of that built-in root defect that you get. Grout. Grout is obviously essential to transfer the load from the base plate down to the foundation below. There's really no reason to use anything but a non-metallic grout unless you have a situation where you have some kind of vibratory condition, like a vibrating piece of equipment or something. You don't need to incur the cost of a metallic grout because it is more expensive. We always like to make the grout strength, as measured by cube test at 28 days, twice as strong as the supporting concrete. Why do we do that? Well, AISC has this square root of A2 over A1 issue where you can increase the bearing stress under the base plate by that ratio of A2 over A1, the square root of A2 over A1, where A1 is the area of the base plate and A2 is the area below the base plate that the load mushrooms out onto, if that area exists. And so rather than check that all the time, we just say let's always use a grout that's twice as strong as the concrete. So for that situation, we're always covered. So that's what we do. Grouting under base plates is not recommended when you double nut the anchor rod that supports the base plate in an outdoor situation. Why? Because the grout can tend to crack, trap moisture, and then the moisture eats on the anchor rod and causes corrosion. That's why if you look at the highway departments, they never grout base plates that have high light poles. They always nut them because they don't want corrosion occurring around the anchor rod and the nut, like it could if you had a grouted situation. Anchor rods, I assume all of you know that the politically correct term is anchor rod now, not anchor bolt. AISC went to the trouble of influencing an entire new ASTM specification, A1554 or F1554, specifically made for anchor rod situations. They come in three grades, 36, 55, and 105. A36 is normally the anchor rod material of choice. It's also good because it's weldable. You can get it in grade 55, which you can order, special order as weldable. Grade 105 is not weldable under any circumstances. You can't even get it that way. We've actually had situations where we've had extremely high tension forces in anchor rods, and we've needed 4-inch diameter anchor rods where the grade 105 wasn't getting us there. And there is another ASTM number in the manual. I forget what it is, but it ends with a grade BD. It goes all the way up to like 150 KSI, F sub U. So you can, in a 4-inch anchor rod like that, you can develop some serious tension. So if you outgrow 105, there is another option available to you, but obviously they're very expensive. And to try to transfer the force from a 4-inch 150 KS anchor rod down into the foundation takes some foundation too. It's how you develop that force down into the pier, but it can be done. Galvanized anchors are used for exposed conditions. Galvanized anchors and nuts should be purchased from the same supplier. It should be shipped as an assembly. Post-installed anchors are suitable only for very small loads and not practical for building columns. I'd really discourage a contractor from letting you use a post-installed anchor unless maybe it's a grouted anchor rod into the foundation, drilled and grouted, epoxy grouted. This new F1554 spec comes color-coded, blue for 836, yellow for 55, red for 105, and if you order 55 weldable, there's a white paint mark at the embedded end. They signify that. Very helpful to put that white paint mark at the embedded end, wouldn't you say? I don't know who dreamed that one up. Nuts and washers have their own ASTM designations. Pretty basic stuff here. We want to talk about column bases that are subjected to axial load, compression, or tension. In some cases you have axial load and shear, like you would have in a braced frame. or sometimes you have axial load in moment like you might have in a moment frame. So you can get into design situations where you have all three of these conditions. Remember that OSHA now has this new requirement for columns and column connections to foundations, where you have to have a minimum of 4 anchor rods that are designed for a 300-pound gorilla located 18 inches out eccentric from the column, to be sure that when that guy's climbing on the column it doesn't fall over and kill him. So no more 2 anchor rod conditions anymore. So all of our typical details have been changed to 4 anchor rods as a minimum, and I trust you would do the same. For the compression condition, obviously we look at base plate design, the bending of the base plate, calculation of the thickness from that bending, and then the bearing of the concrete dictates the size of the base plate. If you have tension, then we have the potential of getting anchor rod tension forces that have to be then embedded into the foundation. And that, of course, influences the base plate design as well as the anchor rod itself. Instead of being 4 nominal anchor rods, now you could have tension that the rod is either bigger or longer because of the tension force. So this series of slides just talks about the various conditions you can get into. All of us are very much aware of the very simple case where you have an axial loaded column compression coming down to a base plate, the base plate rigid enough to distribute the load uniformly over the area of the plate, proportion the base plate for the area, or the concrete stress under the base plate. The new requirement now that came out some years ago is that in addition to the one-way bending about each axis of the plate out from the column, we also have to look at the potential bending of the base plate for more lightly loaded base plates within the perimeter of the column, and that's what this expression right here is trying to do, is to work that potential limit state into the design process. You can refer to AISC specification for section 14, figure 14-3 in the manual as a very good discussion of what we're talking about here. The second situation we're showing there is if you also maybe have that column as part of a braced frame, and braced frames are prone to have very high uplift forces because you can't get much gravity load in them from tributary area, yet they may be receiving a lot of wind load or seismic load from the floors above, and so you could get in an uplift situation. That's kind of common. And therefore we have to design the anchor rods for the tension, and we got to take the load from the column into the base plate into the anchor rod. Now, what we've shown here, I think, works reasonably well if you have very small amounts of uplift. But I learned a long time ago when I designed my first high-rise building that fabricators would much prefer, when you have big columns with big uplift forces, to not take the load down the column over to the base plate in bending through a weld around the perimeter of the column to the base plate. Those are too expensive places to spend money to develop high forces, then over into the anchor rods, but rather you extend the anchor rods up the side of the column, create a pocket for the anchor rod. So now we're taking the load directly from the column, dragging it into the anchor rod, into the foundation, and not stressing the weld around the column base and not bending the base plate. Then our base plate simply is carrying the compression load, which is really good at doing. It's not trying to resist a high uplift force, and therefore that weld around the perimeter of the column isn't near as critical as it was if you try to take a big force, uplift force, through the base plate. So think about the best load path is usually the one that's the shortest load path to the foundation. That's from the column directly into the anchor rods into the foundation, not through the base plate and the base plate weld. But in light loads, what we show here is fine. Obviously, in addition to the vertical gravity load in compression, where we proportion the plate, we also have to think about the bending, reverse bending in that plate from the anchor rods and proportion for that condition, which is what we're showing here. Now, when you're dragging load from the column into the anchor rods, into the concrete, you got to be real mindful of your load path. Back to load path again. This slide just shows the A2 over A1 thing we were talking about earlier, where AISC lets you have a higher allowable stress under the base plate as a function of the area, square root of the area A2 over A1. A2 area is defined as the cone, the 45-degree cone that branches out until it hits an edge somewhere. Wherever it hits an edge, you draw a horizontal line, and that defines the A2 area. Notice that the very low phi factor, 0.65, that is part of the equation for proportioning the bearing. Now, most of you are probably aware, and we're not going to go into this much, but they do get into it in the design guide. ACI 318.02, now 05, has an Appendix D that was many years in development at ACI, which basically covers the design of anchors, both embedded anchors and post-installed anchors. And it appears like the way it's going is that anchor rods for steel buildings are basically going to be proportioned more according to the requirements of ACI 318 Appendix D. And that's the way the new design guide has gone. They're pretty much referring back to ACI 318 Appendix D. So all of us are going to get familiar with ACI 318 Appendix D as it relates to the design of anchor rods and base plates for combined axial load bending and uplift. But B, so I'm not going to get into Appendix D here, but just be mindful that's where you're going to go when you're studying the new design guide. It will send you there. There's plenty of examples worked in that new design guide that will show you how to design for these different situations. One particular one that I want to call your attention to that sometimes engineers miss, you have uplift on a column. And you're taking the load again from the column to the base plate over to the anchor rod, and then uplift on the anchor rod that gets embedded in the foundation. One potential failure path is that broken line we show there. And obviously you can visualize what's happening. The load is being transferred from the anchor rod at the nut at the bottom of the anchor rod into the concrete, and the only thing that's resisting that then is the reinforcing steel that penetrates that crack and goes up to the top of the pier. And if you don't have the proper development length on that reinforcing bar that's hooked, you're not going to carry that high uplift force on the column. So again, load path becomes very important here. And sometimes many engineers have missed the fact that you lose a little bit of the development length because of that inclined crack there. It goes up at 1 to 1.5, so just be aware of that. That's what we're trying to show you in this slide. There's several valid mechanisms for transferring shear at the base of a column. We've always done it using a shear friction concept. ACI 318 in Chapter 11 has always had for many years, has had a shear friction concept. And to me, that's very physical and easy to understand, and frankly makes more sense than just taking shear into an anchor rod. The shear friction concept is that when you put high shear at a base plate, what happens is the base plate tries to move over. The anchor rod creates a little bit of a crack at the top of the anchor of the concrete surface. That little cracked surface tries to raise vertically. That vertical raising of the concrete from cracking creates a clamping force on the anchor rod. And so what happens really is that when you have big shear on an anchor rod assembly, it's not shear that's really resisting. It's not shear in the anchor that's being developed. It's really tension in the anchor. So the concept of shear friction is you're taking a shear force and translating it into a tensile force by a shear friction mechanism. That's what shear friction concept's all about in Chapter 11 of ACI. And that's the way we always used to do it. I understand the new design guide will talk about both methods, that is taking the shear force directly into the rod itself or using a shear friction concept, which basically is based on tension in the rod. Interestingly enough, if you design it both ways, you get essentially the same answer. It's kind of comforting to know. When you have really high shear, you may have to put shear lugs on the bottom of the base plate, or you might have to swallow the column up into the concrete, into the base plate to get more shear area. Or you can take it through the anchor rods itself. There's different ways you can do it. But Appendix D in ACI 318 talks about 3 limit states for an anchor. One is the shear strength of the anchor itself, which is basically just the shearing off of the anchor. But more often what happens is you get a concrete breakout strength of the anchor in shear, where the shear force creates, depending on how close you are to an edge, creates this cracking wedge in the concrete that can cause the anchor to fail. Or less often, the concrete pry-out strength failure in shear. Usually if you make your anchors long enough, like we do in steel buildings where they're 18 inches or 24 inches or 36 inches or even 6 feet long, depending on how big your anchor bolt is, you'll never get this one. This one was really developed in Appendix D primarily for post-installed anchors that are only 3 or 4 inches deep. So this phenomenon usually won't occur for our cases. But Appendix D does talk about proportioning the anchors for pure shear. Here's some of the equations that you'll see in Appendix D. I'll save these for you to look at in the design guide. And again, you'll be referring to Appendix D along with that design guide. For the concrete breakout strength, it's provided a few graphics here to show you what you're designing for. Here's kind of what happens physically, and here's the way it's idealized within ACI Appendix D, this kind of wedged cone, and all the equations that are developed around this assumed failure surface that somewhat matches what happens in real life. You got to be careful when you have a group of anchor rods that you not only look at the breakout failure plane of 2 rods like that. That may not be the governing one, actually. It may be that if you have twice the force with 2 additional anchor rods, that this becomes the failure plane that you investigate. So I'll warn you, the design for these anchor rods, when you have nearby concrete edges, starts to get kind of hairy in terms of the complexity of the calculations. And that's why you're always going to want to write a spreadsheet. I envision that there's going to be a program that's going to come out to do this in the very near future. We've actually written a spreadsheet at our office that does it, because these are the kind of calculations you only want to do them by hand one time. Then you'll convince yourself it has to be computerized, because they're very nasty kind of calculations and also very error prone. The pry-out strength, as I mentioned, usually is not a limit state for deeply rooted anchor bolts, so I'm not going to talk much about it here. If you use shallow anchors, this will be a limit state you have to consider. If you have anchor rods that have combined shear and tension in them, which happens sometimes, Appendix D has a interaction surface, the interaction between shear and axial tension force. Notice that even though it tends to be more of a parabolic or circular surface, the ACI approach has been to linearize it and to give you a free zone there, that if you have a certain amount of shear, a large amount of shear and a small amount of tension, you get to ignore that small amount of tension in the proportioning as represented by that horizontal line or that vertical line before you have to consider the interaction. So that kind of makes it easier for the designer. There's the one acceptable interaction surface, which is obviously elliptical. Here's the linear equation that is also acceptable by ACI 318 Appendix D. I mentioned high shear forces, the different ways to handle that. One with a steel shear lug embedded down where you begin to pick up the bearing area along that surface. Or if you have really high shear, sometimes you have to swallow up the entire base plate assembly where you can pick up some additional bearing area here. This is not the scale, obviously. This concrete edge would probably have to be a lot further away to make that second solution a viable one. What we've normally done is just bite the bullet and design the anchor rods for that shear in a shear friction phenomenon and use really heavy anchor rods as opposed to going to these lugs. Obviously, there's ample opportunity for a concrete contractor to screw that up, right? And also for the weld to the bottom of the base plate to be no good. I can visualize all kinds of problems with these two here, so, you know, hopefully you'll get the contractor to use a template and get the anchor rods in the right place, and then you can design that shear just through the anchor rods itself. We're going to talk about in a minute what happens when the contractor screws up, which they frequently do. I guess many of you, have they had the lecture yet about the field fixes? Is that one? That was yesterday, so you're going to see that contractors can do strange things and you have to get exotic fixes to correct them. Another situation that comes up frequently that some engineers don't recognize is when you have a very heavily loaded column near the edge of a concrete surface, and you can visualize this a little bit like the corbel of a precast member. Big, heavy double T sitting on the edge of a corbel, creating a potential limit state failure plane according to that dotted line. The PCI handbook actually has a situation just like this that you have to design for when you design a corbel. Well, the same thing can happen with a steel column heavily loaded near an edge. You have to worry about that failure plane. How do you design for it? Two solutions here. One preferred, the one I like on the left, you put an edge angle there and a diagonal rod crossing the potential cracking plane, developing its force and tension across that failure plane. That's probably the most direct way. It's also possible to put a hairpin around the anchor rod assembly and drag the force into the slab. You see that solution done a lot in metal building construction. Now for the very complicated case of combined axial load and bending at the base of a column. If you're lucky enough to have only a large axial load and a small bending moment, such that the moment gets converted to P times E, and the P force is within the bearing surface of the base plate, the so-called current area, then you don't have any uplift on the base plate and you have no tension in the anchor rod. And that's the situation we're describing here. The bearing area marked in yellow there can be found by just statics, summing forces about some point, or actually summing forces vertically to solve for this y distance to resist the axial load, which now is at an eccentric. So obviously, if you can, you want to put the bearing area in yellow underneath the center of force there, P sub u. And that's how you proportion it. You still proportion the base plate for bending, just like you would in the compression-only situation. So this situation is pretty easy and easier to deal with when you have low eccentricity. It gets to be a lot more challenging when you have a high bending moment, so that P times E, P is actually outside the footprint of the base plate. Then the equations become a little hairier. In addition to summation forces vertical, you have to sum moments about a point. One place to sum moments is about here. Once you do that, you'll end up with a quadratic solution for this y distance, y being the bearing area here. that looks like this. So you've got your P sub u force is known. You're solving for T sub u and y, the amount of bearing area you need. You know what Q max is. That's the maximum stress that the concrete can carry in bearing. So by summing forces vertically and taking moments about some point, you develop these equations that you then can use to solve for the force in the anchor rod and the bearing dimension y under the base plate to resist that combined axial load of bending. We've actually created a little flow chart here. If you have low bending such that your eccentricity is less than the kern distance, n over 6, nd in the width of the base plate, then you're in the low bending situation, and it's like that first slide I showed you. If it's greater than the kern distance, then you have a much higher eccentricity, and you get into that quadratic equation solution for y, and then after you get y, you can get the axial tension in the anchor rod, and so you go down this load path. You can study this more in that design guide. You'll see these same similar equations.